Hello, I am Harshita Ravindra. Today I'll be presenting my research paper with Professor Jayashree Wilson Nair titled Composition of Geospatial Visualizations for Scale-Aware Views of Multiple Outcome Variables in Population Survey. In this work, we demonstrate the inferences from visualizations using a case study on malnutrition in children under 5 in India. Our work shows that such a visual composition of binary relationship presented in visualization and the juxtaposed layout of such pairwise variable is effective in making inferences from the multivariate spatial point patterns in population data. Outline of the presentation today. Maps are widely used for relying spatial association in trends in population studies and thus are included in such dashboards, which are essentially coordinated and multiple views. While a single variable is visualized on map, some applications require two or more variables to visualize spatial associations in population surveys simultaneously. In our work, we explore different visual compositions which use mathematical operators and composite layouts for visualizing multiple outcome variables in survey data. We propose the use of univariate and bivariate data modeling and representation among composite layouts of interest being juxtaposition and superimposed views. Here we demonstrate the inferences from visualization using a case study on malnutrition in children under 5 in India and Karnataka. There has been a limited work in considering visualization methods for bivariate data on geospatial visualizations. Now we will discuss the methodologies used for visualizing such data. To resolve this gap, we explore the use of composite visualization views which include juxtaposition and superimposition as design patterns for multivariate visualization of population data on maps. In the proposed work, the following comparative levers are used. Juxtaposed views using vector and matrix layouts for visual comparison of geospatial visualization. Superposition layouts for the overlay of geospatial visualization. And C, explicit encoding for difference in distribution of variables considered. Of these, explicit encoding and juxtaposed views use global comparisons and the overlays use the local ones. Methodology. In this work, we use 4 design patterns to visualize the coexistence of contextually related and comparable outcomes of population surveys. The proposed 4 design patterns are essentially different visual composition methods that use different CVVs and data models. Hellinger distance in chloropaths, hotspot using spatial autocorrelation in chloropaths, contour maps and heat map using KDEs, and finally overlay and scale-aware heat maps using KDEs. We further discuss how these different patterns perform with different spatial scale in a geospatial visualization on a cartographic map. We propose a novel method of integration of data pairwise outcome variables to be viewed using a single visualization of a symmetric binary operator. We find the distribution of each political unit, which is district and country and so on, using two-dimensional histograms of its neighbor units. Then the probability distribution distance is computed between two outcome variables for each political unit, thus getting the distance values for all political units. A toy example using gridded cell is shown in the figure. Here, we use the neighborhood matrix for each political unit to create the histogram. The Hillinger distance quantifies the similarities between the indicators across two outcome variables. Spatial autocorrelation relates the value of the variable of interest in a given location with values of the same variable in surrounding locations. Spatial autocorrelation gives room for two main classes of autocorrelation. That's the positive spatial autocorrelation, when similar values tend to group together in similar location, and negative spatial autocorrelation in cases where similar values tend to be disparate and farther apart from each other. The concept of a local indicator spatial association, or the LISA, is seen as having two important characteristics. First, it provides a statistic for each location with an assessment of significance. Second, it establishes a proportional relationship between the sum of the local statistics and the corresponding global statistic. Here in the KDE, KDE is a non-parametric density estimation method used to identify a random location, spatial extent, and intensity. Regions determined to have local maximum density are called hotspots. Here we use the quadric kernel known to perform effectively for point pattern data. The quadric kernel density estimator creates a smooth surface for the variation in the density of point events across the specified area. Heat map visualization is also used to depict the intensity or the hotspots of data of geospatial points, which is generated using color transparency. When a heat map layer is enabled on another layer of a heat map, a merged color of the overlay will appear on top of the map, representing the prevalence of dual form of malnutrition. We are interested in visualizing population statistics in different zooms or scales. That's the country and state or counties. For each scale, the color maps are recommended based on the range of values, thus providing scale appropriate visualizations. Case study. We apply the proposed methods in the case study of malnutrition in children under 5 years of age as captured by the population survey from India, namely the National Family Health Survey, also called as NFHS. For our case study, the outcome variable in the survey are height for age, weight for age, weight for height, growth percentile greater than 90%, and growth percentile greater than 95%, which are indicative of stunting, wasting, underweight, overweight, and obesity, respectively. For stunting, underweight, and wasting, the presence is indicated by the values of lesser than or equal to -2 Z scores. These undernourishment measures are standardized for the malnutrition status of children from WHO. The overnourishment measures in the under 5 population are based on the growth percentiles determined using the body mass index and the biological age of the child. We first visualize the state-wise population distribution for the NFHS survey against the statewide distribution of the latest official census taken in 2011 in the states. We conclude that the sample size from the NFHS for under 5 is roughly proportional to the population in the states. Results. Here we conclude a juxtaposed view for comparing different spatial distribution of a single outcome variable. These visualizations use a vector layout in a juxtaposed view for comparison. The northern belt of India, which is Haryana, Delhi, Uttar Pradesh, Bihar, Jharkhand, and Rajasthan, has a higher prevalence of stunting and underweight. A higher prevalence of wasting is observed in Haryana, Bihar, Madhya Pradesh, and Rajasthan, but weaker than the trends for stunting and underweight conditions. All hotspots in India in LISA cluster maps correspond to high density regions from KDE in India. The districts in Karnataka having a higher prevalence of stunting, underweight, and wasting are observed in Yadgir, Gulbarga, Koppala, Ballari, Bagalkot, Davangere, Raichur, Bidar, Bijapur, Dharwad. The hotspot in LISA cluster maps, which is red, match with the high density regions indicated in both the contour maps and the heat map. We see that the visualization show more details when the scale changes from the national to the state level as expected. But not all high density regions from KDE in Karnataka corresponds to hotspot in LISA clustering. Here in this slide, we compare the unary over nutrition outcomes computed using the global standards of the WHO and those using the Indian growth reference for children and adolescents from Kadil Kawaham et al. In India. More point patterns are captured using Indian growth chart than the WHO growth chart, confirming with the exhaustive study of the overnutrition condition in India. The Indian growth references uses the percentile growth chart based on gender, age, height, and weight attributes. The northeastern regions of India, in addition to the parts of northern belt, has higher prevalence of overnutrition. Here we compare the similar urinary overnutrition outcomes in Karnataka. Northern districts of Karnataka show the prevalence of both overnourishment conditions. We now look at the direct comparison of outcome variables using the binary operator. We then use a matrix layout of juxtaposed view to visualize all the outcome variables simultaneously. Low HD implies either two conditions coexist or two conditions do not exist at all. Thus, we see that for two conditions where both are either under or overnourishment condition, the HD score is low all over India. We also see patterns of a single condition when HD is computed between an under and an overnourishment condition in India. In Karnataka, we observe lower HD score only between the underweight and stunting, indicating similar spatial distribution and also a high degree of coexistence. This is also confirmed by the juxtaposed view of the unary operator. The range of HD values is much lower for Karnataka than in India, even though we observe finer grain differences in Karnataka. The bivariant LISA cluster map gives hotspot that indicate where both conditions are high, thus indicating coexistence. The coexistence of undernourishment condition, that is the stunting and underweight, and wasting and overweight are significantly higher as indicated by the Moroni value. All combinations for the 5 malnutrition condition show hotspots in the central and east regions of India. Northern Karnataka shows hotspots for any two malnutrition condition, and the degree of coexistence is high for most part of the malnutrition condition based on the Moroni value, except for the overweight with any condition. We observe stronger patterns of cold spots in southern regions of both India and Karnataka. For the bivariant KDE heat maps, our choice of color palette for overlay is to use a single color sequence color map based on saturation. The 5 color corresponding to the malnutrition condition are chosen in such a way that they can be distinctly identified even when they mix up with any of the other 4 colors. The northern belt in India prominently shows strong coexistence for any two conditions. In Karnataka, we see sparser point pattern of coexistence between stunting and any other conditions. Otherwise, we observe a larger overlap between any two conditions across the state. In summary, the map-based visualization enable spatial understanding of the existence of different malnutrition condition by design. Unlike the non-visual data analysis method, comparative visualizations using our proposed vector and matrix layout for juxtaposition show the influence of spatial locality. The case study of the coexistence of different malnutrition conditions in the underweight population in India significantly shows the effectiveness of the proposed set of visual composition based on the unary and the binary operator. The work here of visual compositions can be extended to other binary relationship such as correlation and other data formats other than geospatial data as future work. We acknowledge the support of IBM Shared University Grant and the Mathematical Research Impact Support Grant by the Science and Engineering Board, and above are the references for the paper. We thank you for your attention. We close the talk with the conclusion slide. We'll be happy to take questions. Thank you.